Okay, so welcome back to another video. So here's a question from the 2002 Putnam Exam. This is question B3 and it's asked as follows. We want to show that for all integers n strictly greater than 1, we have that the following inequality holds. So we have 1 divided by 2ne is strictly less than 1 divided by e. Subtract 1 minus 1 divided by n quantity to the power n is strictly less than 1 divided by n times e. So with all this context of how the statement's given that we want to prove, this is leaning more in context towards of analysis problem. But this is actually not that bad to show the proof that the inequality holds with the condition. We're leaning towards more, we're going to actually start going backwards. So we're going to start with our given, and then as we proceed forward with this to the proof, that the following mathematical expression written may not be written as the same as the given, like how most proofs you want to, lead towards that goal, but it actually shows that from that last line of expression that the inequality holds for that same condition as well, such that it leads to the same results. So not as bad as it is. This is more of a little easier of a Putnam Exam question that personally I think, or a lot of you might feel the same way as well compared to how some other questions asked in terms of the context of analysis problems. But using a little bit of algebra and some other formulas we'll be using, mainly there's a specific series we'll be using to help utilize the following for this procedure. So anyways, other than that, let's actually just jump right in. So just like any algebra problem with a compound inequality, let's actually subtract specifically the term 1 divided by e to both sides of our inequality. So of course this is going to lead that this is 1 divided by 2ne, then subtract 1 divided by e is strictly less than negative the quantity of 1 minus 1 over n, and then to the power n, which is strictly less than, so subtract 1 over e to both sides, so to the right hand side. So 1 divided by n times e, and then subtract 1 over e. So let's actually now fix this up and divide this negative to the both sides. And what that does is, of course, that'll change the sign. So I'll actually just rearrange the term. So the leading term is a positive. So that would mean we have 1 divided by e, then subtract 1 divided by 2ne, which is, but of course, with the negative sign that we divide, so that hence means that we have to switch our sign. So this is going to be now turned into a greater than 1 minus 1 divided by n and to the power n, which is strictly greater than 1 divided by e, and then subtract 1 divided by n times e. So next what I'll do now is I'll multiply e to both sides of our entire inequality. And I'm actually just gonna rearrange the signs. So for one, this is gonna now write as far as the left hand side, this will be on the right hand side, and of course this will be in the middle, and then of course the signs will change. So this is gonna be 1, then subtract 1 divided by n, which is strictly less than, so this is going to be e, and then multiply with 1 minus 1 over n, and then to the power n, then less than 1, then subtract 1 divided by 2n. So let's now take the natural log of the entire compound inequality, which is nice that this is actually monetarily increasing, which the inequality still holds from that. So this will yield us the natural log of 1 minus 1 over n, then strictly less than. So I'll take the natural log, so I have ln of e times this entire thing over here, then using properties of natural log, so ln of e of course is just going to equal 1, then move that n to the front of the exponent, so this is going to be plus, and then ln of 1 subtract 1 divided by n, which is now less than ln of 1 subtract 1 divided by 2n. And so here's the series that, as I mentioned, that we're actually going to be using, and this is a very handy tool that be using, especially in any sort of proofs that if you're dealing with inequalities, where anything in general. But the following Taylor series we're going to be using is that notes that the negative natural log of 1 minus x is going to equal to this power series representation. So this is an infinite series starting with n is equal to 1 of x to the power n, and then divided by n. And of course, this is actually going to be convergent for x in the following open interval from -1 to +1. And so that's nice that that holds. So we'll be using that. But next, so now let's actually multiply -1 to the previous sequence of inequalities. So of course that's actually going to change the signs again. So that'll be put back as a greater than. So now this will become the negative natural log of 1 minus 1 divided by n. This is going to be now greater than. So this will turn out to be a -1, then subtract n times ln of 1 minus 1 over n, of course then being greater than negative ln of 1 subtract 1 divided by 2n. And now we can actually use our Taylor series to actually rewrite the entire inequality over here. So this will convert to the following. So this is going to be the infinite sum from n is equal to 1. Well, I'll actually put this as k is equal to 1 since everything in our term is with n. So k is equal to 1 of, now we just have to put in the inputs right here. So that's easy to do. So it's just 1 divided by n, then to the power k, then divided by k, which is greater than. So now this is going to be negative 1, then add this with n, and then multiply with the infinite sum. K is equal to 1 of 1 divided by n to the power k, then divided by k. It's just the same thing as over here, so that's fine. Then now greater than the infinite sum from k is equal to 1 of 1 divided by 2n, then to the power k, then divided by k. And now let's actually just simplify some things a little further. Well, what I mean is distribute the k into the exponents for whatever in the base. So this is going to be the infinite sum. K is equal to 1 of 1 divided by, so of course this is just being k, and then multiply with n to the power k, then greater than. So what I can do here is I'll actually rewrite this entire expression over here with a different, and then re-indexing as well. So applying all this, so I'll just save you the work. If you want to verify this yourself, go for it. So we have that this is k is equal to 2 for the index of 1 divided by n, then to the power k subtract 1, and then divided by k. Then this is greater than the infinite sum over here. K is equal to 1 of 1 divided by k, then times 2 to the power k, then multiply with n to the power k. And so now all we have to do here, let's actually re-index this. So first, this is the left-hand side and the right-hand side don't change. So k is equal to 1 divided by k to the power, or k times n to the power k. And then this is going to be greater than. So re-indexing, so we're going to have 1 divided by n to the power k, and then multiply with k plus 1. And then now greater than or equal to, so that doesn't change on the right hand side over here. So 1 divided by k, then 2 to the power k, and then times n to the power k. And so actually we're pretty much done with the proof, because if you notice that this inequality holds true specifically for k to the power, or I'm looking at it this way. This inequality over here, the last line expression holds true for k times 2 to the power k is strictly greater than k plus 1, and k plus 1 is strictly greater for k, such that k is greater than or equal to 1 for the as a quantifier for verifying this whole inequality. So that actually completes the proof over here. And let me actually, as I said that, let me actually add that to the adjustment to make sure that this actually holds the validity to that. There we have it. So this actually adds a little bit of justification for this entire line over here, which actually holds true. And so going backwards, of course, we have just verified that this following given expression is indeed true as well. So that actually completes the proof, just like that as I underlined with the box. And so there you have it. So yeah, that's pretty cool if you ask me.